Yeah, my name is Nick Randall. I'm going to talk to you about a few recent applications of in-situ small-scale mechanical testing, specifically for reliability and failure analysis. So just as a small introduction, let me see if I can, there we go. So Alemnis is originally a spin-off of EMPA in Thun in Switzerland. We're located just below Bern in Thun. This is the view from our office. And this is a little bit the evolution of the company. We started around 2000 with the first in-situ mechanical tester that could be put into a scanning electron microscope so that you can actually see what's happening when you're making a mechanical test. So what is an in-situ test? You can see it here. So this is an indentation into a bulk metallic glass, actually. And you can see the load displacement curve doesn't necessarily tell us what's happening at the interface, whereas being able to see the test live with the SEM shows us that we actually have some slip planes here. So the system itself is small. We have an indenter mounted on a displacement actuator here and a sample mounted on the load cell. The sample is typically on a standard SEM stub. So it's very easy to mount. We either glue or clamp it. So this is used a lot already in typical nano indentation testing of, for example, bonding pads you can see here at the bottom, because we can locate a zone to a few nanometers precision. So we're very, very accurate in our repositioning accuracy. So just to show you what this looks like. So here's the Alemnis standard assembly mounted on the XY stage of an SEM. We're just mounting the indenter here. And then we're going to mount the sample, which is glued to an SEM stub, which you see now. And once we have sample and indenter in place, the whole assembly can then be moved under the pole piece of the SEM. So here we see just tightening of the grub screw. And then the whole assembly is going to be moved inside the chamber. And then we shut the door, pump down a vacuum, and then approach towards the pole piece. Here we go. And once we're focused on the surface of the sample, we can then choose where we want to make a test. In this case, we're looking at a micropillar that's been made by focused ion beam, so a fibbed pillar. And we might want to do a single cycle stress strain analysis to see when the pillar breaks. This is a silicon micropillar. Okay, there it goes, it breaks. Or we can program the system to do whatever we want. In this case, we're doing a fatigue test. We can do this low cycle, high cycle. We can choose the amplitude, etc. So you get an idea of how the system works. Okay, we can either mount it in the SEM on the left here, or we can take it outside the SEM and have it use it as a standalone, very similar to a standard nano indenter mounted vertically. So here's some examples of how you might want to use this type of test. So top left is a single nano indentation, so conventional nano indentation where we're cracking the surface. This is actually gallium arsenide to measure the fracture toughness. Here we've got a micropillar of a 4-stack coating. So there are 4 coatings here. We've cut a pillar and we're measuring the stress strain properties. We can use the system in tension as well as in compression. So we can fib very small tensile specimens with gauge widths of a few microns. We can do scratch testing. Down here, we've got a pillar with a pre-crack. So we can actually drive cracks in the uniaxial direction. This is 3D printed small structures. These are springs being tested, but could have application in semiconductor as well. Beam bending, often coupled with EBSD. So we can look at dislocation movements, and lateral testing, almost tribology. So a wide range of test techniques that can be used. One important point is different to most nano indenters, this system is a displacement controlled machine. And this is very important for deforming large structures. You can see here, this is a 3D printed structure. If this was a load controlled experiment, as soon as we start to crush, we're going to suddenly crush very fast and not get any data. So it's very important to have displacement control in order to have constant speed and therefore the entire deformation history of the material. So a quick overview of different speed testing, because this is quite unique. When we test at different speeds, we can look at the strain rate sensitivity of materials. And at the moment, typically nanoindenters are testing in very slow regime speeds, typically -1, -2 down here. And what's interesting is this red box. So getting up to strain rates of 10 to the 4, 10 to the 5, which are very fast. And we do that by being able to deform very quickly. So typically using a piezo mounted here that can deform the indenter at up to 10 millimeters per second. And we do that on a very small pillar, which is a few microns. And therefore we can get up to strain rates of 10 to the 5, so 10,000 per second, which is the speed almost of a bullet hitting something, right? So it's ballistic. And this allows us to map strain rates over many orders of magnitude. And just to show you why that's useful, this is a fused silica pillar. If we deform this pillar very slowly, it's glass, we get a ductile result, right? So at 0.0008 per second and 0.008 per second, we've got very ductile deformation, which is normal. If you deform glass very slowly, it deforms in a plastic way. If we go to the next order of magnitude, 0.07 per second, you can see now that we're failing the pillar and we've got some serration. So we're actually seeing the ductile to brittle transition of the glass. If we go to the next order of magnitude, 0.7, now we're very brittle, and we see that in the data. So we break more quickly, and there's very little ductility. If we go to the next order of magnitude, 6 per second, now we're still brittle. This is the most brittle state, and there's no ductility at all, pretty much. So we might assume that if we go faster, we might become even more brittle, because if you hit a piece of glass with a hammer, it smashes, right? You don't get any ductility coming back. But at the small scale, we see that at 60 per second, we're still brittle, but we see some ductility coming back. So this is the 60 per second, this is the 850 per second, and this is 1,400 per second. So just on this slide, we've got 8 orders of magnitude of strain rate on the same material. And that really is new today, being able to look at the strain rate sensitivity, especially in semiconductor materials that might be subjected to high strains in service. So we can also couple that with environmental control. So we have external to the SEM, we do liquid testing, we do humidity control. We can also do radioactive control and high and low temperature. So just to show you quickly a high temperature stage, here we're heating the sample and cooling it. And we're heating and cooling the indenter separately. And we bring them together so that we have a stable thermal contact. And just an example from semiconductor, here we have silicon micropillars being tested at 500 degrees C. Now, we assume that silicon is a very brittle material, but when we deform it at high temperature, we see it's actually pretty soft and ductile. You can see it's a very slow test, 0.001 per second. These are all done with different strain rate jumps. So here we're still testing because it's a very slow test. Let's go to the next one, 0.01. So you can see here, ductile deformation of the silicon pillar. You can see necking occurring, but we don't actually fail the silicon. We just deform it in a ductile way. So let's let that one run, go to the next one. 0.1, this is the ductile to brittle transitions speed. We see that very clearly. And then as we go faster, we've got 1 per second, we've got 10 per second. Now we're very brittle. We're just seeing the before and after because we're moving very, very fast. So you can see that silicon has very different properties depending on the speed of deformation. And of course, that's very linked to the temperature of operation as well. And here you can just see a summary of that. So on these silicon pillars, we did testing from cryo temperatures, so very low, -30, up to 500. And you see this ductile to brittle transition very nicely on the stress strain curve. Another way we can use the system is for rapid impact. So for shock testing, here we've actually got tests on a coating up to 100,000 hits with a flat punch, and at 2 temperatures, room temperature and 500. So we can see how the material reacts to repeated impact on the surface. This is how we do cryo, so low temperature. So we're actually cooling the system by pumping liquid nitrogen into the SEM chamber. And here we've got a fused silica pillar being tested with a multi-cycle at minus 120 degrees C. So a nice example. Another recent innovation is high-speed mapping, so the ability to make large arrays of nanoindentations over a defined surface and actually see what's going on. So we can do that because we have very fast electronics for the strain rate. So you can see a typical fast map being performed here with a Berkovich indenter. And you can see how this might be useful because on a metal microstructure, for example, this is the SEM image. We've done 10,000 indents in this square area. And so this is the hardness map. This is the modulus map. And you can clearly see the blue grains are the molybdenum disulfide, which is very soft, so low hardness. And the red grains are very hard. These are the carbides in the microstructure. So in the case of semiconductor, we're often interested in making fast maps to check coating properties. This is a bonding pad coating, and we're doing small, fast arrays of maps in different areas on the bonding pad to understand the integrity of the aluminium coating, which is deposited on the pad. And of course, we've got to be very localized because we don't want to test where there's a scrub mark. We use the humidity control module for testing packaging. So typically MEMS packaging where we might have popcorn cracking. We can simulate different humidities and actually compress and do a compression test of the whole package. So these are tests on PMMA at 30, 60, and 90% humidity. We can also put the system in a modified frame for beamlines, so we can do tests in synchrotron beamlines or in tomography units. And we feel this is a way forward where we could test mechanical properties and measure the 3D tomographic image. So this is a system placed in an RX Solutions CT scanner. This is a polymer foam. We're compressing it from above, and while we compress it, we're rotating and building the 360-degree image of that foam structure. And this could also be very interesting for looking at semicon packaging. Also, this is another example of tomography, compressing a particle to a predefined strain, so deformation of 100 microns, and then doing a 360 scan to look at the cracking inside. This could also be a useful technique. So moving on, some other techniques. Scratch testing is commonly used for looking at coating integrity. It's been mentioned briefly before, and it's nice to actually be able to see the scratch in real time. You can see the tensile cracks here being formed. And when the load is removed at the end, you can see the viscoelastic recovery of the material. Look at that. So it's a very nice way to understand not only scratch resistance, but also viscoelastic properties, surface scratch resistance, and it can also be used in progressive load for looking at scratch adhesion to the substrate. Okay. These are some dedicated structures made by focused ion beam for fracture toughness in 3 modes. So single beam with a pre-notch, so mode 1 deformation, right? Mode 2, so going against the crack axis, and you can see small cracks being produced here. This is all silicon material. And mode 3, going actually perpendicular to the axis. So these can be used for specific fracture toughness calculations. Another way of doing it is to make the indents and measure the crack lengths. So you can see here we're cracking in gallium arsenide, and then we can put the crack lengths into this simple equation. So F is the load, C is the crack length, E over H is the modulus to hardness ratio, and these are the crack sizes. And this gives us Kc, which is the fracture toughness of the material. And you can see some very nice cracks in this picture on the right, and also a video of some ring cracks being created with a spherical indenter, also in gallium arsenide. So look at this when we unload the indenter here. You can very nicely see those cracks recovering. Here we go. So it's recovering now. We're removing the load. Look at how this bottom part closes up. Look at that. So nice example. We can also do impact testing, as I mentioned before. This is simple impact on a silicon wafer, just so you can see how cracks propagate in the material. This is an example of using impact for shock testing. So this is an accelerometer, capacitive accelerometer. So we're basically simulating the suspended accelerometer part hitting the stoppers. And so we're basically repeatedly hitting the stopper and seeing how many cycles it takes to fail that material. This is a bump shear test. So we're using the lateral force measurement of the system to rip off a single wire bond. And we do that using a special truncated indenter. And it's very nice to see this in real time because we can see how the bond is failing and where exactly at the interface. And we can also couple that with electrical testing at the same time. One thing that's useful is combining the mapping advantage with arrays of pillars. So we're able to make arrays of pillars, especially in semiconductor materials, using lithography. If we did them by focused ion beam, it would take days and days. But we can make an entire wafer of pillars in the space of some hours using lithography. So this means we can program the machine to test every pillar with different parameters. So we can very quickly and in an automated way, get a lot of data to put into our models. So this is an array of silicon pillars. You can see one being failed on the right here. And here you can see an automated test where we're basically going to every pillar and testing each pillar with slightly different parameters. So you could have some pillars, for example, on different areas of your wafer around devices. And as a quality control tool, you could be testing those pillars just to be sure that the material or the coating hasn't changed in properties and you don't have a production issue. We also use mapping to look at interfaces, of course, bonding lines, all types of different areas. This is actually the interface between two materials. So you can see the depth is constant of our indents, but we can see we're going into a softer material here because we've got more pileup of the indents around the indents. You can see the map to the right here. This is also an automated platform development to be able to fast map different areas of a 4-inch wafer. So you could have a whole range of devices on there. You could choose areas under the microscope and then go under the indenter head and in an automated way map different areas, different bonding pads, different devices, different packages even. So that's something that we're currently developing at the moment. One application is these are capacitive accelerometers still at the wafer level. And so we can drive around and choose certain devices, there's thousands on this wafer, and do a beam bend test, as you can see here. So we're basically increasing the load until this beam breaks. So you can see the load increase and the failure. So using this as a fast automated quality control tool. We can also map through sections of bonds. So this is looking at the coating and the bond wire. We can also look at different areas of the bond wire. And this is simulating the actual probe testing by actually mounting a probe on the Alemnis system and then being able to apply that probe. For example, here we're doing it on PN junctions and we're functionalizing the indent, the probe tip, with a closed circuit. So we can also look at the electrical properties and the load at which connection is made. So just a couple of final slides. The other things we have developed recently is a smaller version of the Alemnis system that fits into the Hitachi desktop SEM. So this may be of interest in some fabs. We also have coupled our nano-indenter module with an AFM. And we heard earlier in Silke's talk about the use of AFM in situ in an SEM. Well, with this system, you can not only look at the zone of the SEM, you can image it with the AFM, and you can make nano-indentations in specific zones of your choice. So you can see here an example. This is a high-speed steel microstructure. You can see the backscatter images, the AFM image of the surface, and then we've made some indents in specific grains. So we're really moving towards correlative microscopy techniques where we combine mechanical properties, AFM topography, SEM, EDX, and trying to combine all these in the same area with the same spatial resolution. So thank you very much. Just a few conclusions. Alemnis, we continue to push the boundaries of small scale testing. Strain rate control, I think, is very unique, as is the temperature, high temperature and low temperature, and also being able to do very, very fast mapping. Currently, we're up to about 10 indents per second. So the question then is, we have the instrumentation to go very fast, but does the test at that speed really make sense? If we want purely mechanical properties, then maybe 10 indents per second is a bit too fast. But if we just want to compare a surface and map it, then it can be quite useful because we get a lot of data points very quickly. And of course, integration in desktop SEM and the combination with AFM. So thanks very much. And if there's any questions, please don't hesitate to get in touch. There's my email address.
Yeah, thank you very much, Nick, for this very visually appealing presentation. It's very nice to see these live videos, and visually it's very aesthetic. So we have time for some questions, and then we'll go into the discussion panel as well, where we can have some more. So does anybody have any questions on Nick's talk? Otherwise, I have a couple to start with, because I could see, obviously we do a lot of mechanical testing in AFM as well, but it's at a different scale. I was trying to look at the scale bars for the end radius of some of the probes you had that look like between 5 and 10 microns. So maybe you can talk about the probes you have. Are these commercially available probes? Do you make them yourselves? What are the typical size ranges you have?
Well, standard indentation, if I just go back to an indentation test. So for nano indentation, we're using a Berkovich, which is a 3-sided pyramid, right? Yeah. As you see here. This has an angle of 137 degrees, and the best tip radius you get on a Berkovich is about 10 to 20 nanometers, okay? So even this pyramid has a radius at the apex. So it's not the same as an AFM tip. You're never going to get the same resolution. But we need a tip area with a defined geometry so that we can calculate the contact area and therefore get mechanical properties like hardness or modulus. So it's a compromise. Okay.
And some of the other push tests, the cycling test, you're not using the pyramidal face, you're using a different type of...
Yeah, so for pillar compression, we'd be using a flat punch. And the whole point of the flat punch is that we, so on the end of this is a flat punch, right? So that we don't have to worry about the contact area changing. It's always the same. We basically have a flat on flat contact, right? And so we have a fixed contact area. And so we can take that error out of the equation for stress strain. But we can basically make any shape indenter and a wide range of materials. We can make the indenters conducting, non-conducting, doped. And that's why we also developed the combination of AFM, so that we'd have the advantage of AFM imaging with the mechanical properties dedicated test. Because with AFM, of course, you can measure mechanical properties, but it's difficult to know the exact tip area shape in order to get the mechanical property in a quantitative way.
Okay. And I have one other question. If I'm not mistaken, you said the displacement that you're doing in Z here is done by piezos. What is the range of displacement that you can have?
So we have three ranges, 20, 40, and 100 microns.
Okay.
Yeah. You've got to have a fairly big range, because if you're testing soft materials, then for a few millinewtons of load, you might be moving tens of microns, for example, in polymers. So you need to have a fairly wide displacement range.
Okay. We have a question in the back here.
Fraunhofer, IASB. So I'm very much excited about the nano indentation inside the SEM, or Matthias Rommel in the focused ion beam. What temperature ranges you can do in the chamber? Is it the same like the external one?
It's actually higher. So we're helped in the SEM because we're doing high temperature in a vacuum. So we don't need to worry about heat loss by convection. We only have to worry about radiation loss. So we have modules going up to 1,000 degrees in situ. So we can go up to 1,000 maximum temperature and down to about minus 150 using liquid nitrogen.
Now, when I refer to the CSN method I explained earlier, I would also have the chance to make an array or a line scan. That would be possible in situ as well?
Of course.
Okay, very nice. Yeah. Thank you very much.
Okay. Any other questions on site here? Do we have any offline?
If anyone's interested in lab testing, we have a lab testing service as well. So get in touch, we can do some tests on your materials.
Okay. So it's already 11:50, which is the time for our discussion panel. So that way, if there are any other further questions for Nick, we can ask obviously during this time. But if any of the previous talks, even from this morning, we'll be happy to try to answer any questions people have. I know that there was a question from Sika Lee. If you're still available to ask your question, please feel free to do that.
Hi, can you hear me?
Yes.
Oh, okay. My question is for Alexander just now regarding the KPFM. I would like to know for the KPFM results for graphene, you showed the results for air and in vacuum. How about if it's measured in glove box? Would there be a difference? How different it is? Because I know you mentioned that's the concern of the water.
Yeah, hi, Sigli. Good question. We haven't done any measurements on these kinds of samples in a glove box. However, we can flood our high vac chamber with the different inert gases. For example, we can flood it with argon or with nitrogen, and then also influence the humidity level in that regard. However, the water layer on most samples is quite resilient, and just by simply flooding the system with inert gas, it's kind of hard to remove all the water content. So we usually even sometimes apply an annealing stage or step within the vacuum to really remove all the water. Yeah, so I can't really give a more precise comment than that.
Thank you very much. Because currently, for the SPM systems, most of the makers are mentioned that it's sufficient just to perform the measurements in glove box. So I just wonder how difference with how the measurement results be if it's performed in glove box and vacuum. If you have any information next time, I would appreciate to know about it next time.
Gladly so.
Thank you very much.
Thank you.
Yeah. So Alex, actually, I have a follow-up question on that for you, because you mentioned that you did the measurements in the high vac, obviously to try to get rid of the influence of any humidity on there. Did you also do a bake of the sample while it was inside the high vac to eliminate any of the moisture or not?
For this kind of sample, we did not bake any of the sample at elevated temperatures. We simply let it rest over a longer period of time while vacuuming the chamber and establishing really stable content. However, we can, of course, introduce the seating station within the high vac and then anneal the samples. But for this experiment, we didn't.
Okay, thank you. I had seen also, yes, Dr. Minge has his hand raised. So if you have a question.
Yes, the question is to Alexander again. Sorry, I have several questions. I couldn't get the last point regarding the possibility of annealing inside the high vac. Can it be done already, or it is something not possible yet?
Yeah, we can do this. We have a heating stage that we could also fit within the high vac and then anneal samples basically while applying a vacuum. This should be possible. Yeah, we can do this.
Then I saw that you had some nice results with the possibility of illuminating the samples with different wavelengths. Is it possible for you to elaborate a little bit about your setup? Is it inbuilt to the tool that you can already align the lasers or the LEDs, or do you need something external?
It is basically an external light source, laser source. It's almost looks like a small laser pointer that you can electrically wire to the controller and then control via software. And it's basically a small little tripod that you can point to a sample. And then you can choose the different wavelength, of course. But you can also use the superluminescent diode of the cantilever observer, basically, to slightly disalign the laser point alignment on the cantilever to illuminate your sample more fully.
All right.
Yeah.
Okay.
Sorry, the module itself is external.
I see. Then there was one question regarding your time result experiments. Of course, couldn't see any. We didn't have a chance to see the results. But could you tell us something about the time scale of your measurements? Are we talking about in the order of milliseconds or seconds?
Good question. We can have different time scales. So of course, seconds and milliseconds we can do. If I'm not mistaken, our time resolution is 40 microseconds.
Is it with the same internal current amplifier you have, or is it?
Yeah.
Okay. All right. And I think towards the end of your slides, you showed some results with Moire patterns of graphene on HBN. Were these at room temperature measurements or something special were done to get those high resolution images?
These were at room temperature.
All right. All right.
Some of the experiments have been done in our high vac at inert gases, but the temperature was always room temperature.
All right. Thanks a lot. Results were very, very interesting to us. Thank you very much.